Welcome to the first video of Chapter 12. Chapter 12 covers vectors and the geometry of space. So the big difference between Calculus 2 or Calculus BC and Calculus 3 is that instead of working in 2 space, we're going to be working in 3 space. So this first video is really the background of 3 space. We're going to cover 3 main objectives. First, we're going to look at the rectangular coordinate system. So you've done that before in 2 space, x comma y. So we're going to look at what does that look like in 3 space. And then defining distance and equations of spheres in 3 space. So let's just jump right in, starting with the first objective, which is to look at what is the rectangular coordinate system in 3 space. So before we look at 3 space, let's just review what you have worked with most of the time, which is 2 space. 2 space is just the standard XY coordinate plane. So that's 2 space, that's what you've done before. What we're doing in 3 space is we're going to be looking at points defined by x, y, and z. So in this space, x, the x-axis, is going to come out towards us, almost like it's out off of the plane. And then we have y-axis, and z is going to go up. So what I've drawn is I've drawn the positive x, y, and z axes. So the negative z-axis would keep going down like this, then the negative x-axis goes back, and then the negative y-axis would go here. So this is negative y, this would be negative z, and this would be negative x. So a few pieces of vocab that go along with 3 space is we have the xy plane. So you've seen that before, that's the plane that's defined by the x and y axes. And then we're going to have the YZ plane. We're going to have the XZ plane. And then the last one, if you remember back to 2 space, we looked at 4 different quadrants. Quadrants 1, 2, 3, and 4. Well, in 3 space, we don't have quadrants, we have octants. So you're going to hear me refer to these planes and then refer to octants, the octants that points are in. And so that's just some basic vocab. And so the first thing that we're going to do with this new coordinate system is we're going to do some graphing. But before that, I want to introduce you to what is called the right-hand rule. So here's how we determine the z-axis. So which way the positive z-axis is. The positive z-axis is determined by what we call the right-hand rule. If you curl the fingers of your right hand from the positive x to the positive y, and you can do that with me now, positive x to positive y, your thumb points in the direction of the positive z-axis. You're not going to need that too much right now, but later on after this video, when we start moving into vectors, we're going to need to be able to determine the positive direction of the z-axis. And so just keep that right-hand rule in your back pocket for later. Okay, so now that we know what this 3 space XYZ looks like, we are going to do some graphing. So first example that we're going to do is we are going to graph the point 2, 3, 4. So this is telling us that x is positive 2, y is positive 3, and z is positive 4. So the way you're going to do this is you're going to start by just drawing out your axes. So here's my positive x, here's my positive y, here's my positive z. I wouldn't bother to draw out the negatives because we don't need any of those axes. So first thing, this point is going to come out 2 on the x-axis, and then it's going to go over 3 on the y-axis. So I come out 2, I go over 3, and you kind of have to picture this. So the point comes out the screen towards us, and then it heads to the right. And then what it's going to do is it's going to go up 4 points on z. So it's going to end up somewhere about here. Now, this is really difficult for a lot of people to picture, and so oftentimes what I suggest is if you can draw a prism to denote where that point is, it helps gives us a little bit better perspective. So here would be the bottom of the prism, and then if I come up, this is the front of the prism. And so hopefully that makes it a little more clear where that point is. So it came out 2, over 3, up 4. So that's the first point that we're going to graph. now we're going to graph that point in example 2, where we're going to look at some negatives. Our x this time is negative, our y is positive, and then our z is negative. So I would start the same way that we did before. Draw out the positive x, y, and z axes. And it might be helpful to label them if you want to, but you certainly don't have to. Okay, so we know that we're going to be using negative x. That x is going to be going backwards from us. So here is our negative x, and we also know that z is going to be negative. And so here's where I would start to do a little bit of scaling. X, we're going to go 3 spots for. Y, we're going to go 2. And z, we're going to go 6. And then we're ready to get started. So our point, starting at the origin, is going to go back 3. It's then going to go over 2. And then it's going to go down 6. So this is about where that point is going to land. And again, this is a little hard to picture, and so I would again suggest that we draw in this prism to give us a little bit of a better idea of where this point ends up. Doesn't have to be perfect. Most of us are probably not the best artists, which is fine. But there's that point then. So we went back 3, to the right 2, and then down 6. So that's the basics of what we're going to be looking at in terms of the rest of this course, is in that 3-space system. So next thing that we want to be able to do is we want to be able to find the distance between 2 points. And so you're going to notice that's our next objective, and we have this distance formula here in 3-space. It's not going to be a surprise, or it shouldn't be shocking. It's going to follow the same formula that you saw in 2-space. So based off of Pythagorean theorem, we're going to find the difference in our x's, find the difference in our y's, find the difference in our z's, and square them. So what we need to do is we need to find the distance between the points in the 2 examples above. So if we're going to find that distance is going to be equal to the square root. If I subtract my x's, I have 2 subtract negative 3, subtract my y's, so 3 subtract 2, subtract my z's. So that ends up being the square root of 5 squared, add 1 squared, add 10 squared. So we get a distance of the square root of 126. Okay, so then the next thing that we're going to do, where this leads us to then, is the equation of a sphere. So at the top, you're going to notice the equation of a sphere, so a circle in 3-space. And again, it shouldn't shock you. It's very similar to the equation of a circle in 2-space. You're going to have your center be that x naught, y naught, z naught. So what I mean is x naught, y naught, z naught is the center of the sphere, and r, like it was before, is the radius of the sphere. So there we go. We're going to do a few examples with circles because this comes up in a variety of ways. And then the last thing that we will be doing in the video is talking about some graphing. So example 4, write the equation of the circle with a diameter having endpoints of -1, 2, 1, and 0, 2, 3. So we need 2 things to write the equation of a sphere. Sorry, this shouldn't be circle, this should be sphere. So we need 2 things to write the equation of a sphere. We need the center and we need the radius. And we don't have either of those. So first thing I'm going to do is I'm going to find the center of this sphere. And you're just going to use the midpoint formula like you did before. Add the x's, divide by 2, so that gives me -1/2. Add the y's, divide by 2, which gives me 2. And add the z's and divide by 2, which gives me 2 again. And then you have a few different options to find the radius. You can jump into the equation, you can use the distance formula, whatever you prefer. So I'm going to find the radius using the distance formula. And I need 2 points. And so the points that I'm going to use are this center that I have and one of the other points. So the difference between -1/2 and -1 is 1/2. Difference between 2 and 2 is 0. And difference between 2 and 1 is 1. So this gives me the square root of 1/4 plus 1. So my radius then is the square root of 5/4. So at this point, I'm ready to write my equation. I'm going to have x plus 1/2 quantity squared, y subtract 2 squared, z subtract 2 squared is equal to 5/4. So that's using the equation of a sphere. If you remember back to when you used equations of circles, one thing that you also did is you took the equation of a sphere in what we call standard form, or really the equation of a circle in standard form, and you found the center and the radius. So that's what we're going to do in example 5. We have this equation that we're given that is not really in a nice form, but it has everything squared out and whatnot, so it's not as easy to identify the center and radius of the sphere. So in order to do this is going to be a little bit of a throwback for some of you. We're going to have to complete the square. Complete the square. So what I'm trying to do is take the equation that I have here and get it in terms of a more friendly equation. In order to complete the square, I'm going to start by rewriting the equation so that I have my x's together, my y's together, my z's together, and that 17 on the other side. So I have x squared subtract 2x. I'm going to leave myself a space to complete the square. Plus y squared subtract 4y. Again, leave myself a space so I can complete the square. Plus z squared plus 8z. That 17 I don't need, so I'm going to move it to the other side. And I'm going to add 3 spaces for when I complete the square. Okay, so the way to figure out what you're going to add in order to complete the square is you take that b term, you divide it by 2, and you square it. So I'm going to get a 1, and if I add a 1 to the left side, I have to add a 1 to the right side. Now, if you don't remember completing the square, you might be asking yourself, what's the point of that? The point is that hopefully now these x's, or the x with the -2x and the 1, is going to be a perfect square binomial. So if I were to factor that, it's going to become x minus 1 squared. So that's the goal. That gets us closer to an equation of a sphere where we can readily identify the center and radius. Same thing for y. So I take that -4, divide it by 2, and square it, so I get a +4. And again, the idea is if that was correct, then this should become a perfect square binomial, which it is. That's y subtract 2 squared. And then lastly for z, if I take 8 divided by 2 and square it, I'm going to be adding 16. And that will then become z add 4 quantity squared. And if I simplify, I just end up with 4 on the right side. Now, from this equation, we can readily tell that the center of the sphere is 1, 2, -4, and we can tell that the radius is 2. Okay, so then hopefully that made sense. We have one equation to talk, or one theorem to talk about real quick, and then we are going to be looking at doing a little graphing. So the theorem that you can see at the top, an equation of the form x squared add y squared add z squared add gx add hy add iz add j equals 0 represents a sphere, a point, or has no graph. Well, this relates to that example that we just did above, which was in that form, and we saw the sphere. So that's great. Now the question is, how would we have an equation in that form that gives us a point, or one that has no graph? So think about that for a second. How would we have an equation of that form that gives us only a point, or that gives us no graph at all? Okay, hopefully we can tell we would get a point if the equation gave us a radius of 0. So if we had a quote-unquote sphere where the radius is 0, then all we're left with is the center. No graph would occur if we had a radius that was negative. If we would have a radius that was negative, because that's not possible. So if you see equations like that in your homework, don't automatically assume that they're going to be a sphere. Instead, what you're going to have to do is complete the square and see what you get for r. Okay, last objective for this video is to define cylindrical surfaces. Define cylindrical surfaces. So what we're going to be doing with that is we're just going to be graphing in 3 space instead of 2 space. So if you look at example number 6, we are going to be graphing y equals 3 in 3 space. So that's what this is. This denotes 3 space. So you might have been used to seeing that. That's 2 space versus 3 space. So we need to graph y equals 3, keeping account of 3 space. Now my suggestion would be start with 2 space. So let's start with just the regular graphing that we've done before, where we just have an xy plane. Y equals 3 then is just a horizontal line. So then the question is, what happens to that horizontal line when we introduce z? So now if we draw on our axes again, we have our x, y, and z. If we consider where y equals 3 is, that would be this line here on the xy plane. But then what happens is it goes up and down because of z. It goes up and down because of z. So this is going to be not my best drawing. I'm not a great drawer. But if you can imagine, we have a plane. So in words, we would say in 3 space, y equals 3 represents a vertical plane that is parallel to the xz plane and 3 units to the right of it. So hopefully you can picture that. My drawing is not amazing. Okay, we're going to do one more together, and then I'm going to give you an example to try. So example number 7 is similar. We're going to describe and sketch the surface in 3 space represented by y equals x. Okay, so it might be helpful to start in 2 space, but if you're ready to just jump right into 3 space, we can. Okay, so y equals x is going to be on the xy plane. So like we did before, I would start by ignoring z. Ignoring z and show where is y equals x. Well, y equals x is going to be this line right here. But then when we take it into 3 space, that line is going to go up and down along the z-axis. So what we're going to end up with, again, is a plane. Excuse my poor drawing. So we would say that in 3 space, y equals x is a vertical plane that intersects the xy plane in the line y equals x, and then where z is 0. Okay, so we are going to add on at the end of this chapter with some more complicated figures, but it's really important that we are able to draw or at least picture what these figures look like, because that's going to help us when we go on in Calculus 3 and add on. So we have 2 more examples to do, and then we will be finished with this video. If you're up for it, I would ask that you try example number 8, and I'm actually going to change it. I want this to be x squared plus z squared equals 1. X squared plus z squared equals 1. If you're ready, pause the video and give it a try. If you just want to go along with me, then keep watching. So I'm going to start with drawing my axes in. So I have x, y, z. So we need to know x squared plus z squared equals 1. What does that look like? Well, on the xz plane, this is going to be a circle. So what I'm going to do is I'm going to start on the xz plane, ignoring y, by drawing in a circle. And now what we're saying is that the y-axis doesn't matter. This circle is going to be the same no matter where we are on y. So we move to the right on y, the circle is the same. We move left on y, or negative, circle's going to be the same. And then it does keep going. I just don't have the ability to draw that. So what you should have ended up with is a cylinder with a radius of 1 that is parallel to the y-axis. Okay, and then last example in this video, we are just describing a graph. So we're not going to actually draw it. We are describing this graph. So hopefully you notice right away that that x squared plus y squared plus z squared, that represents a sphere. That represents a sphere. So if we start by looking here, we have a sphere of radius 2 that's filled in. Sphere of radius 2 that's filled in. But then as soon as we denote that part, that means we're taking the center out. So the center where the radius is 1 out. So putting that into words, we are going to say that this represents the region between the spheres centered at the origin with radii of 1 and 2. Or you can say it's a sphere with a center cut out. So then, what if we add the condition that z has to be less than or equal to 0? That z is less than or equal to 0. Well, that condition will give us a hemisphere. It would be the lower half of the figure only. Okay, so that was the first set of notes for chapter 12. We just looked at basic 3-space, distance, equation of spheres, and some graphing. In our next set of notes, moving on, we'll be taking a look at vectors. Thanks for being with me today.